Physics Part 112. Another expression of the ideal gas equation, or of a Boyle's law, Charles' law, or a Gay-Lussac's law combined is PV over T constant, or P1 V1 over T1 is equal to P2 V2 over T2. There are few section questions. On a day when the atmospheric pressure is 102 kPa and the temperature is 8 degrees Celsius, the pressure in a car tire is 190 kPa above the atmospheric pressure. After a long journey, the temperature of air in the tire rises to 29 degrees Celsius. Calculate the pressure above the atmospheric of the air in the tire at 29 degrees Celsius. Assume that the volume of the tire remains constant. Number 2, a helium-filled balloon is released at ground level where the temperature is 17 degrees Celsius and the pressure is 1.0 atmosphere. The balloon rises to a height of 2.5 kilometer where the pressure is 0.75 atmospheres. The temperature is 5 degrees Celsius. Calculate the ratio of the volume of the balloon at 2.5 kilometer to that at the ground level. A metal box in the form of a cube of side 30 centimeter is filled with air at atmospheric pressure 1.01 into 10 power raised to 5 Pa at 15 degrees Celsius. The box is sealed and heated in an oven to 200 degrees Celsius. Calculate the net force on each side of the box. Microscopic model of a gas. At the end of this section, we should be able to describe a simple kinetic model for solids, liquids, and gases. We should be able to infer from Brownian motion experiment the evidence for the movement of molecules. We should be able to state the basic assumptions of kinetic theory of gases. We should be able to define the terms of pressure and the use of kinetic theory of a gas to explain the pressure exerted by a gas. We should be able to use the kinetic theory of a gas to deduce the relationship P is equal to 1 over 3 Nm C square over V, where N is the number of molecules. We should be able to compare PV is equal to 1 over 3 Nm C square with PV is equal to NKT, hence deduce that the average translational kinetic energy of a molecule is proportional to T. One of the aims of physics is to describe and explain the behavior of various systems. For mechanical systems, this involves calculating the motion of the parts of system in detail. For example, we have already seen how to predict the motion of a stone thrown in a uniform gravitational field. Using the equation of uniformity accelerated motion, it is not difficult to calculate the position and velocity of the stone at any time. However, there are some cases in which it is quite impossible to describe what happens to each component of the system. This sort of problem arises if we try to describe the properties of a gas in terms of motion of each of its molecules. This difficulty is that the number are so large. 1 cubic meter of atmospheric contains about 3 into 10 power raised to 25 molecules. There is no practical method of determining the position and velocity of every single molecule at a given time. Even the most advanced computer would be unable to handle the calculation of the motion of such a very large number of molecules. We'll continue with the same. That's all for the morning. Bye bye. See you later.